method that we talked about last class. Name? Peyton, and your last name is?
Van Blair.
Down there. Thank you. So the name? Say again?
Ray O'Loughlin.
And what's your last name?
Blackman.
Oh, right there. Gotcha. Thank you. Ray. Name? Jesus. Last name? Was that with an L?
Yeah.
Gotcha. All right. Let's do math. So last week we talked about finding volumes with the disk method, and the first technique we're going to look at today is using a washer technique. Well, let's go to the pictures first. So the washer technique is very similar to the disk method. It's basically the disk method twice, because we're trying to find the area of a washer. So remember that the concept is that we've got our solid object, and we're taking these cross sections, and if we can find the area of a cross section, the integral of that area is going to give us volume. So we integrate area to get volume. And so when we look at this, if we were to take an integration element right here at a random x, when that rotates around the x-axis in this case, it creates this washer. Looks like that. And the area of a washer is basically a big disk minus a little disk. So it's a generalization of the disk method. So the area of that washer is the big area minus the little area. That gives us the blue area. Make sense? So if we can find the area of the washer, then we just integrate that area and we will get the volume. So the integral of a disk, or excuse me, the area of a disk is pi r squared. So they use an r sub 0 or an r sub o to represent the outer radius. Some books will use a big R and a little r. This book uses an r sub o and an r sub I for outer radius and inner radius. Doesn't matter what you want to use. Whatever works. And so that's where this formula comes from. And they factored the pi out. So this is pi times the outer radius squared minus the inner radius squared. That'll be the area of a washer. Anyone know the mathematical word for a washer? There is a math term that refers to it. The word washer is not a math term. Anyone know? So that is called an annulus. An annulus is the mathematical word for a washer, an annulus. But all these calc books will refer to it as a washer. Okay, so let's try one. So we have these two curves here, and we are told that we're going to rotate that region that's trapped or bounded by those two curves. We're going to rotate it around the x-axis, creating, some weird shape. And we want to find the volume of that weird solid of revolution. We're going to call them solids of revolution. So I'm going to start by drawing a representative integration element. I'm going to draw a vertical element at a random x. You can draw it anywhere in the region. But do note this, that if we're going to create a washer, we have to draw our integration element perpendicular to the axis of rotation. All right, so we cannot use a horizontal element if our goal is to create cross-sectional washers. If our integration element was horizontal and we were rotating about the x-axis, this would not create a cross-sectional washer. This is going to create something that we are going to refer to as a cylindrical shell, which we will do later today. If we want a washer, the integration element has to be perpendicular to the axis of rotation. Same as for a disk. If we want to create a disk, the element has to be perpendicular to the axis of rotation. So a cylindrical shell is going to be the only time where we can choose a parallel element, an element parallel to our axis. So we have to use a vertical element here. And when that vertical element rotates around the x-axis, it creates the washer. Let's identify the inner and outer radius. So we can imagine these 2 points. This distance right here, this is representing the inner radius. And let's go with a different color. This distance right here is representing the outer radius. So however you want to indicate it, you can use, you don't have to use braces, you can use lines or whatever you want, dashes, dashed lines, whatever you want. Somehow you just have to, in your mind, identify the inner radius and the outer radius. So then we are going to use our geometric formula for the area of a washer. So last class we were using the area of a disk, and now we're going to use the area of a washer. The area of a washer is pi times the outer radius squared minus the inner radius squared. So here is our generic formula for the area of a washer. Now, we chose a vertical element. We imagine that element as a thin rectangle. We imagine that as a rectangle that has what for its width or its thickness? dx. So vertical rectangle, thickness is dx. Horizontal rectangle, thickness is dy. So that tells us, that is our indicator for what the integral should look like. It should have a dx in it, which tells us the integrand should have only x's. Right? You can't integrate with respect to x something that has y's in it. You need x's. So that's just an extra indicator that we want our functions presented as y values, because a vertical distance is the upper y minus the lower y. The upper y value is written as x's. The lower y value is written as x's, so that's going to give us x's minus x's with a dx. So that's how we're going to proceed. So our volume is going to be pi. That can factor to the front. And then we're going to have the outer radius, which is this function, so that's x to the 1/4 quantity squared minus the inner radius. The y value is equal to x, so minus x squared. Dx is going to be the question?
Well, so what if you don't have a graph? Like, how would you find out which one's the outer and the inner?
So it's always going to be, with all of these, it's going to be really helpful to sketch the graph, because it's not always obvious what's the outer and what's the inner, or what's the right and what's the left. So you want to be able to sketch a graph.
Okay.
90% of the time you can sketch a graph. Now if it literally is just 2 curves and you know one of them's the outer and one of them's the inner, you could just go through the math, and if you end up with a negative, you know that you just chose wrong, right? Because if you did them backwards, you would just end up with a negative answer instead of a positive answer. We know we're finding area which will be positive, so you could, do it that way also. I would recommend drawing a graph though. Sketching the graph gives you a sense of how the curves are oriented, gives you a sense of what you should expect for your limits of integration. So I would definitely focus on the graph. Yeah, sure. Okay, speaking of that, we now have to put in our limits of integration. So those limits of integration are the x-coordinates of the intersection points. So we want to find the x-coordinates of the intersection points. So we're going to set these 2 curves equal to each other. So we're going to say x to the 1/4 is, so that's the y value here. We want to know where they share a y value right there. They share y values right there. So we're going to set the 2 y values equal to each other. And then we're going to get the x coordinates of where those functions match. All right, so we raise both sides to the 4th power. We have a nonlinear equation, everything to one side and factor. Typical strategy. Does not matter which side you go to. And then we factor. And then we solve using the 0 product rule. and x will have to be 0 or 1. So that tells us both intersection points. That tells us that they intersect at x equals 0 and x equals 3. Excuse me, x equals 1. So those will be our two limits of integration. So we're integrating from x equals 0 over to x equals 1. So when we're thinking about this integral conceptually, we're saying, oh yeah, we've got all these washers that are kind of stacked sideways, and the integration symbol is summing up the volume of each of those. So remember that what's inside here is a cross-section, and this cross-section has no thickness. Cross-section is two-dimensional, but then we throw in the thickness, and this is what gives us volume. Bless you. So now this whole thing is the volume of a slice. And our slice in this case has the shape of a washer. And when we do the dx, it just adds thickness to that washer. So it creates a miniature volume, a tiny volume. And then the summation symbol, the integral symbol sums them all up. Adds up all the little volumes to get the total volume. Okay, so now let's do the integration here. Let's move this down a little bit, give us some space. So we're going to have pi, and let's simplify what's in here first. So this is going to be x to the what? X to the 1/2. Power to power, you multiply the exponents. Power to power, you multiply. So if we just simplify the look of our integrand a little bit, we're going to have that. And then we use the power rule. The power rule, whenever we have a power of x, the power rule, we add 1 to the exponent. Please, please, don't do it. So power rule for both those terms. Then we plug and chug, plug in the upper limit, plug in the lower limit. And we end up with 2/3 minus 1/3. So we end up with pi over 3. That's our volume. Any questions on any step? Okay, let's do another one. All right. Once again, we're going to rotate around the x-axis. Once again, we want a washer. So the element that we're going to choose, the integration element, this thin rectangle, it's going to be vertical. We'll say that that's an integration element at a random x. When we rotate it around, it creates a washer. We want the area of a washer. All right, the area of a washer, we know that that's pi times the outer radius squared minus the inner radius squared. So we're going to come back over here. We're going to identify the inner and outer radius. So this one right here is the inner radius. This one right here is the outer radius. So the outer radius is going to be the curve that's above. It's going to be the upper curve. So this will be pi multiplied by x plus 2 quantity squared minus, once again, the inner curve is x, so it's just x squared. So that is the area of the washer at x. That tells us our volume will be the integral. Pi can factor to the front, so pi times the integral of, we'll square this out, and they give us our limits of integration. They tell us that we're going to go from 0 to 4. So no mystery there. No simultaneous solve. Limits are given. And of course, we'll combine like terms so the x squareds will vanish. And then we have two terms that we can integrate using the power rule. So the power rule says add 1 to the exponent, divide by the new exponent. So we will end up with pi multiplied by 2x squared plus 4x on the interval 0 to 4. Plug and chug. Plug in 4 here, we get 16 times 2, which is 32, plus 16. Subtract off 0, so we'll end up with 48 pi. Any step there? You're not sure about? Oh, look reasonable. So again, our main concept is find cross-sectional area and integrate. And we're going to have 3 different basic shapes for our cross-sectional area. We will have discs and washers. And then later today we'll do a shell, which is just a cylinder. So let's try it the other way. So the formula looks identical. We have pi multiplied by an outer radius squared minus an inner radius squared. So same setup. If we were doing a disk with a integral that has a dy, it's the same idea. The area of a disk is pi r squared. It's just that when we are using a dy, we deal with functions of y instead of functions of x. So let's talk about terminology for a moment here. So when we look at this function here, this is a function of x. So when we say a function of x, x is the independent variable and y is the dependent variable. Right here, this is a function of x. So when we have a dx, we have functions of x that we're subtracting typically. When we have a dy, we have functions of y, which we are going to subtract. Right function of y minus the left function of y. So there's different ways to sort of talk about this. You can say that that's a function of x, or you can say it's a function that is presented as a y value. Right? The way we look at that, it's y equals, so it's like a y value. We're saying this is what y is equal to. So you can think of it as either a function of x, or you can think of it as a y value. So let's go ahead and do this sideways. So we're going to integrate with respect to y instead of with respect to x. And everything looks the same as it did with the other direction. You just have to identify the inner radius, the outer radius, and then write them both as functions of y. In other words, write them as x values. Because if you're doing horizontal subtraction, you subtract x's. Right x minus left x gives you the distance in between. So let's try. So we have these functions here. They tell us, let's rotate around the y-axis, and let's use, in this case, it will turn into a disk. But we are going to use a horizontal element. And so here, let's notice, there is a horizontal element at y. Here is a horizontal element at a random y. This region, that green region, is touching the axis that you're rotating around. So the cross sections are going to be disks because it's touching. There's no hole in the middle. Down here, when we rotate that blue horizontal element, there's a gap, right? There's a gap right here. And so when we rotate that around the axis, we are going to create a washer. So this one is going to be a disk method. This one is going to be a washer method. So everybody seeing the difference? So if the region's touching the axis, there's no gap, which means you're going to create a disk and not a washer. If there's a little gap, then that element is swinging around with a hole in the middle. So then you're going to create a washer. So that one we're going to do using the disk method, the other one with the washer method. Now, in both cases, we are dealing with a horizontal element, and horizontal distances are determined by x values. These functions, all four, everything here is presented as a y value. Well, if we know we're going to use a dy, which we do, because the thickness of a sleeping rectangle is dy, we know everything needs to be in terms of y. So that's one way to think of it, is that if you have a dy, all the functions need to be in terms of y. The other way to think of it is that if you're going horizontal, you are taking differences of x values, so you need to solve all the functions for x. Either way, you can think of it in either way. So when we look at this situation here, red is on the left, black is on the right. So we need to have the red curve and the black curve written as x values. The x value on the left there is x equals 0. That's the left curve. The curve on the right, y equals natural log of x. Okay, we need to rewrite that as an x value, so that's x equals e to the y. So now we have the right curve and the left curve written as x values. So now we can take the difference and find that horizontal distance. How about down here? Let's just pay attention to one step at a time. So this is the left curve. This is the right curve. Both curves are presented as y values. So now we want to isolate x, or solve for x, or present them as x values, or present them as functions of y. Lots of different ways that you can say what we're about to do. So this red curve right here, written as an x value, is y over 2. This curve here, written as an x value, not too hard, I guess, in this case. But we would just switch the order and write it as an x value. X is equal to y. So now, when we switch this, what we're saying is y is the independent variable, and x is the dependent variable. Down here, y is the independent variable, x is the dependent variable. X depends on y, x depends on y, x depends on y for all those. So now we've rewritten everything as functions of y or as x values, however you would like to think about it. So let's go for the disk one up here. So dealing with the disk, we know that the area of a disk is pi r squared. That is the area of a disk. So now we have to come and look at our picture and decide what's the radius. Pi radius squared, what's the radius? So the axis of rotation is the y-axis. The radius is the length of this blue element that we drew right there. It's whatever that length is. Well, that's a horizontal distance. Horizontal distance is right x minus left x. Right? Does that make sense to everybody when I say that? If you're thinking about an x-axis, and this is at -3 and this is at 5, if you want to know the distance in between, the distance in between is the right x minus the left x, which will give us 8. Right, so horizontal distance, right minus left, vertical distance, upper minus lower. So we look at our picture and we figure out what's to the right and what's to the left. And here, the x value on the right, that's this curve. There's the x value on the left, the red curve. X value on the right is e to the y. X value on the left is 0. So this is pi multiplied by e to the y quantity squared. Question?
So you really don't have like a set radius then, right? Like an exact answer for that.
The radius is a function of x. Because you can see that as you draw your horizontal element in different places, that distance is different.
Yeah.
So the radius is a function. So the exact radius is e to the y, exact in quotes, because it depends on where you draw the element. Yeah. So yeah, you're right. It's not a number.
Okay.
And how do we simplify e to the y squared? 2y. Bless you. So e to the 2y, right? So once again, we have power to power. Power to power, you multiply. Power to power, multiply. And volume is then the integral. And we can factor the pi to the front. We're going to integrate e to the 2y. So e to the y, e to the 2y, and then we multiply by dy. That's the thickness of this horizontal rectangle that we see right there. That's a rectangle. And limits of integration, they tell us the vertical limits are going from 0 to 2. Here is a classic reverse chain rule. So when we look right here, if we were going to use substitution, we would let u be 2y. And we could go through that process. Of course, it's going to work. But what we talked about last week and what we want to focus on in this class, because we will be doing about 1,000 integrations that have linear substitutions, we don't need to go through those 3 steps because the same thing happens every time. So we use reverse chain rule. So reverse chain rule, RCR, if you have a linear substitution, you can use RCR. You can use reverse chain rule. So let's do that. So reverse chain rule says, instead of multiplying by the derivative of the exponent, you divide by it. Yeah, that's it. So this is going to be itself, e to the 2y, divided by 2. So reverse chain rule, we just divide instead of multiply. And we are ready to plug in our limits of integration. So let's see. I'm going to factor the pi over 2. I'm going to think of that as a constant in front. Constants can always be moved to the front. And so my focus for the antiderivative evaluation is just going to be on this part. So it's going to be pi over 2 multiplied by the antiderivative part here that I'm looking at the upper limit, which will be e to the 4, minus e to the 0. And e to the 0, of course, is 1. So this will be pi divided by 2 multiplied by e to the 4 minus 1. So that will be our answer. All right, any step there you want to look at more carefully? All good?
On a test, do you care in which form you have the answer? If it's like fully factored or fully like.
No. So there's no rule for what simplified means. Generally, it's whatever's convenient. It's nice to put things in factored form if you're looking for zeros or something, because then you can find the zeros really easily. Numerically, that's totally fine. If you expanded it, that's totally fine also. It doesn't really matter. That's not gonna, yeah. It's a little bit ambiguous when you talk about it. Okay, so let's look at this one. Same basic idea. Question?
Sorry, back to the first one. How did you, know to solve it in terms of,
With respect to y?
yeah.
Because the element is horizontal, and how thick is a horizontal element? dy or dx if it's horizontal. dy for a horizontal element, and for a vertical element, the thickness is dx. So that's a real clear hook into the problem. Oh yeah, vertical element, we're going dx. That means everything inside the integral has to be an x. If we have a horizontal, it's dy. That tells us everything in the integral has to be a y. So you can only integrate with respect to y, an expression of y. You can only integrate with respect to x, a function of x. So here we integrate this expression in x with respect to x. So they always have to line up. So I think that's a really good way to think about it. Draw your element, and that's just a real clear indication. Oh yeah, it's going to be with respect to y. If it's vertical, with respect to x. So that's definitely where I would sort of think about making that association.
And is that what you were saying about it has to be perpendicular for the washerman?
Yes. So this element here is perpendicular to the axis of rotation. And so if we're creating a washer or a disk, the element has to be perpendicular to the axis of rotation. And then we look at the direction of the element, and that tells us whether it's going to be a dx or a dy. So first we think about the geometry. If we want to create a disk or a washer, that's got to be perpendicular. If we wanted to create a cylinder, it would be parallel. So we first think about, are we going to use the disk or a washer? What direction should the element be? Oh, if it's a washer and we're rotating around the y-axis, we have to have an element that's horizontal. That then tells us, oh, dy, horizontal rectangle has thickness dy. That then tells us that everything inside the integrand has to be a y inside the integrand.
Is it always gonna tell you like you're gonna rotate about this axis, or
Yes.
are you ever gonna give us? Okay.
Yeah, there won't be ambiguity there. They will say, take the region and rotate about the x-axis, rotate about the y-axis, or you could rotate about a random axis. They might say, rotate around x equals 5. So then we still are going to use the same geometric principles, but the axis and the distances will be found in a slightly more complicated way, which we will get to shortly. Okay, so here's our washer then. Now that we have our washer, we then think about the basic geometry. The area of a washer is pi times the outer radius squared minus the inner radius squared. So this is our basic geometry. Now we have to look at our graph and say, well, what's our I and what's our O? So we come back over here and we have to identify, and however you want to identify it can get very messy. So sometimes you don't even want to write stuff on there because it starts to get too messy. But the inner radius is going to be the closer function to the axis of rotation, and the outer radius will be the further function from the axis of rotation. So the red curve is going to be closest to the axis of rotation, so that's going to dictate the inner radius. The black curve is further from the axis of rotation, so that's dictating the outer radius. And so now our outer radius, so we just said that's the black curve. So now here we have to be super. Sometimes you look at this expression, x equals y, that equation. It's simple looking, but it gets a little more complicated when it's just x equals y. Like up here where, okay, you know which side of this you're plugging in. That's the function side. Here you've got to just be careful. You think in your head, sideways rectangle, only y's on the inside, so that should be what we plug in, not x, but the y. So this is going to be the outer radius squared. And then this function's a little more obvious. So the x value over here is y over 2. So the inner radius is going to be y over 2. So this will be y over 2 quantity squared. Do you want to shut that door? Sounds like they're watching videos. That's not a math class. We're not watching anime videos. Okay, so then that will give us the area of the washer at y. And so this gets at what we were talking about a minute ago. There's not a consistent, this element here, this sideways blue element, right? It changes length as you move through here, which means those washers are changing in area. So this is giving us the area of the washer at y. So if we wanted to, we could say, hey, what's going to be the biggest washer? The biggest washer is going to be the one, let's choose that color. So right here, right, this is going to create the biggest washer right there. So when that rotates around the y-axis, that creates a washer. And if we wanted to know what the area of that corresponding washer would be, we would plug in 6 for those two y coordinates right there. And notice that at the very bottom here, where we have the two curves meeting, the y values are 0 here for both curves. Plug in 0 here and you get a washer that has area of 0, which is what we would expect. So that gives us the area of the washer at a height of y. And now we can find our volume by integrating that area function. And once again, they tell us what the limits of integration are. We're integrating with respect to y. So we have that as our setup before integration. Common denominator, let's go ahead and simplify the integrand, and then we'll integrate after we've simplified it. So that's going to be 3y squared divided by 4 times dy. You could factor out the 3/4 if you wanted. We can just integrate directly, though. Either way will give you the same answer. So y cubed over 3, the 3's will cancel. So we're going to get y cubed and 4 in the denominator from 0 to 6. Let's plug in the 6. And I'm just going to write it in this way. It's 6 cubed. And we're dividing by 4. It's just going to be a little easier to simplify here. We're going to take out a 2 there, make that a 3, take out another 2 there, make that a 1, make that a 3. So whatever that simplifies to. So that is the volume. Any questions? Yeah.
I already said it like 10 times, but
That's all right.
it's rotate about the y. We're going to like integrate it with respect to y. And this horizontal element x for the element y. Or sorry, other way around.
Yeah, the first part that you said was right. If we're going to rotate around y, we're going to have a dy.
Okay.
If we're going to rotate around x, we're going to have a dx. And the only change to that is going to be when we do the cylindrical shell method. So if we're doing a disk or a washer, what you said is right. Rotate around y, dy, rotate around x, dx, yeah. And so it all depends on the relationship between the integration element and that axis. If they're perpendicular, then what you just said is right on. Vertical element dx, horizontal element dy. And then when we get to the shell, we'll change it up a little bit. When this just seems too easy, we'll change it up. Okay, so here is a region, and we're going to rotate around the y-axis. So the axis of rotation given up here to be the y-axis. And I just graphed this in Desmos, and I'll do this from time to time just so you can kind of see how you would graph in Desmos. Desmos is super easy to put a restriction. You just use braces, and this restricts it so that your graphs aren't going all the way, beyond each other. You can narrow them down very easily with those restrictions on whatever letter you want to restrict, x or y. So it's a nice, easy way to graph a region. And we're going to rotate that about the y-axis. And we're going to create a washer. So we're going to use the washer method. So as soon as we know that we're using the washer method, we want to think about the area of a general washer. So we know that a washer has this formula for its area. And then we go to our picture and we identify where the outer and inner radius is. And so here we're thinking about this distance right there. That is the inner radius. And then that is the outer radius. Does that part make perfect sense? So the inner radius is always the closer curve. The outer radius is the further curve. And when you're thinking about your integration element right here, you're sort of going to either the left end point or the right end point of your integration element. So the area then can be found by writing the two curves that bound the element. So the black curve on the left is bounding the element, and the blue curve on the right is bounding the element. We want to write both those curves as x values, in other words, as functions of y. Okay, so the curve right here is y equals square root of x. All right, that's written as a y value. We want to isolate the x, though, so we're going to write that as x equals y squared. That is our inner radius. The inner radius will be y squared. The outer radius is simple. What's that x value? X equals 4. Right, that right curve, that blue curve is a constant. X equals 4. So that curve is, there we have so you can think of it this way. Wherever you draw your representative element, isn't x equal, it's always the same curve on the right. It's always at x equals 4. So there's nothing functional about that right boundary. It's a constant. It's always going to be at 4. So that allows us to rewrite our general area formula for a washer. We can write it with the specific functions we have here. Outer radius, we just said, is 4. The inner radius is y squared. And so we'll have y squared squared, which is y to the 4th. And here's where you just want to keep in your mind, horizontal rectangle, thickness is dy. So we're integrating with respect to y. All these should be y's over here. Shouldn't be any x's commingled in there.
So even though x equals 4 doesn't involve a y in that equation, if we're integrating with respect to y, you can still just take it?
So think of it this way. When we're finding a horizontal distance is x value minus x value. This x value is equal to 4. This x value is equal to y squared. Right? Does that make sense? So the x value on the right is always 4. The x value on the left is always y squared. So those x values, functions of y, or possibly constant. The other direction, functions of x, or possibly constant. Yeah. So the volume can then be found by integrating 16 minus y to the 4th with respect to y. And we can see in this case that the y values are going to go from 0 to 2. You could plug in x equals 4 right into that and see that that height is at 2 if it's not obvious. So you take the square root equation right there, y equals square root of x. Take x equals 4, plug it in there, and you get square root of 4, which is 2. So we know that that upper y coordinate is 2. All right, any questions up to that point? Because that's the hard part. The integration part's pretty straightforward with the power rule. Yeah?
You had mentioned earlier that if it was like x minus 5, that there'd be more math involved in terms of finding the base superposition or finding that effect.
Yes.
In this type of question and the other examples that we've done, we've always had a 0. Can that be shifted and that wouldn't affect the math? Is that the same thing?
If the whole region was shifted,
Yes.
if the whole region was going to be shifted, then this curve right here would take into account the shift. Right, the shift would be built into this function. So if we shifted to the right 2 units, we would have the square root of x minus 2 here.
Okay.
If I said, maybe I said that. I think I said that right, but
Okay, yeah, okay.
So it would
change the bounds, and then it would change when
in this case, if we just shifted to the right, it wouldn't change the bounds. The bounds would still be 0 to 2. It would actually change the function. But we would still be going 0 to 2. If we took this whole region and shifted it over, we're still going to be between y equals 0 and y equals 2. It's just that that function, y equals square root of x, would have been shifted over here. So this would be where the shift would take place. So shifting could change the bounds, or it could change, it has to change something. You could, if we shifted it up, that would change both. It would change the bounds, because now we're no longer between 0 and 2 if we shifted this whole thing up. it would change the bounds, but it would also change the functions because the function would be square root of x plus something.
Okay.
So yeah, as soon as we shift it. The basic rule of thumb is looking at your picture and the axis of rotation, everything is relative to the axis of rotation. So if your shape was over here, your inner radius still goes to the closer curve, your outer radius still goes to the further curve. So the basic relationship would be the same. Yeah, we'll look at an example of that later today for sure, where it's a little more complicated. So then we can integrate this very simply using the power rule. Power rule makes us happy. And plugging in the 2 is the important limit of integration there. So we end up with that. And then we can factor out the 32 is a pretty quick way to do this. If you factor out the 32, you're left with 1 minus a fifth, and 1 minus a fifth is 4 fifths. That's a nice simple way to not have to get a common denominator of 5. Factor out the 32, and you're left with 1 minus a fifth, which is 4 fifths, and then we are going to have 128, I think, at pi over 5. Any other questions on that one? Make sense? Sometimes it just makes perfect sense. And the more you look at these, the more they start to make perfect sense.
Why is the upper bound 2 and not 1?
So 1 is right here. And if you think about think about those horizontal elements. You want to think about the collection of all horizontal elements. There's a horizontal element at 0, there's a horizontal element at 1/2, and all the way up to this y value of 2, all the way up to here. You can imagine this stacking of horizontal elements. It doesn't matter where you draw your representative horizontal element, but we can imagine all these horizontal elements going from y equals 0 up to y equals 2. Does that make sense? Yeah. So the one that we draw, we usually draw it kind of in the middle, but you can draw it anywhere. That horizontal element is just a representative element. And the limits of integration take into consideration all possible horizontal elements, wherever all of the possible ones all at once. Oh, here we go. Rotating around a different axis. So, you ask and you shall receive. So that line, y equals 1, we are now rotating around that line. Our axis of rotation is now right here. All the basic geometry is going to hold. Vertical distances are still upper minus lower. Horizontal distances are still right minus left. We're still going to use those basic principles. It's just that we're going to apply it to a slightly more general scenario. So they give us the graph right there. That's y equals 1 minus the square root of x. And then the region that we're going to talk about is bounded by y equals 1 and x equals 1. So that creates the green region. That's the region bounded by 3 curves. And we're going to rotate about that curve. So if we want to create a disk or a washer, what direction should the element be? Vertical or horizontal? Vertical element. So the axis of rotation is horizontal. So if we want to create a disk, the element should be touching the axis of rotation. If we want to create a washer, there should be a gap. But in either case, that element is perpendicular to the axis of rotation. So we know that our representative element, let's draw it right there, has to be vertical. If that element went horizontal, we would end up creating a cylinder if we rotated, not a disk or a washer. So there's our representative element. I'm going to say that that's the element at a random x. So this will become important once we get to the cylinders. But it's good in your mind, if you think about a random vertical element, it's at a random x. A random horizontal element is at a random y. So we'll usually label the vertical element at x, horizontal element at y. It will become much more important when we get to cylinders. Okay, so are we creating a disk or a washer? Which is disk. Why is it a disk? It is a disk because the element is touching the axis of rotation. If this region was rotating around the x-axis, this would create a washer because there's a gap right there if we were going to go about x. Right, there's a gap. But there is no gap between the element and the rotation axis. If there's no gap, it's touching it, so when it rotates around, it's creating a disk. Right, there has to be a gap to create a washer, to get the hole in the middle. Okay. Now, the length of that element is going to be the radius of the corresponding disk when that's rotated. So if we've got our axis sitting there and we've got our element down there, when it rotates around, whatever the length of that element is, that's our radius. And it's going to change. Right? When we look at that radius, depending on where we draw that vertical element, the radius is changing. So the radius is a function. The radius is going to be a function of x. All right. So now we think to ourselves, okay, vertical element, upper y minus lower y. Right? A vertical distance, when we're doing a vertical distance, it's always upper minus lower. If you imagine a vertical axis, and this is 7, and this is 3, we know that that distance is 4. We do upper minus lower y values. So y values. All right. So if we want our radius, and the radius is a vertical distance, we have to do the upper y value minus the lower y value. The upper y value is 1. Right, that y value up there is 1. The lower y value is this function, 1 minus root x. So it's upper minus lower quantity squared. So this y value right here, that's that y value, and that is that y value. So the y value up top is 1. The y value down below is the 1 minus root x. And here's where we have our little check. Say, oh, vertical element thickness is dx. Everything over here should be x's, because dx means integrate with respect to x. So everything in the area function, the only variable should be an x. All right, so then we simplify this area function a bit. We're going to distribute the minus. 1 minus 1 cancels. The minus makes that a positive, so we end up with just pi x when we square it. So that is the area of the disk at x. Let's just check that our area function makes sense. When we imagine the biggest possible disk, it's going to be the disk at x equals 1, because this radius is the biggest. Of all these possible radii, the biggest one is there. And what is the area of a disk of radius 1? Pi. Let's check. If we plug in a 1 here, do we get pi? Yes. The smallest disk is this disk over here that's not really a disk, because that pinches down to a point, so when it rotates around, we should get an area of 0. Well, the x value is 0. We plug that in there. Sure enough, we get 0. So that area function is building the area of each one of those disks for all the x's between 0 and 1. And now we can find our volume by integrating the area function. So we are integrating with respect to x because we have a thickness of dx. And they give us our limits of integration 0 to 1. So those are from the x-axis, not the y-axis. Those are from the x-axis. And this is pretty straightforward. We're going to get a pi times x squared over 2, 0 to 1, and that's going to be pi over 2. step there. So that definitely a little bit more kind of analyzing. But we still are using the same basic principles. If we have a vertical element, upper minus lower y value. Horizontal element, right minus left. Still using basic concepts. It's just a little more complicated setup. Okay, so here's another one. Here we're going to go around the line x equals 4. So here is our rotation right there. So we've got our region that we're rotating. So our capital R, that's this region over here. It's bounded in between these three curves. X equals 0, y equals 2, and square root of x. So that region is bounded in between the three curves. We're going to rotate it around. Element has to be perpendicular to the axis. So this is our general element at a random y. So random element at a random y. Washer or disk? Washer or disk? Washer, if we're going to go around here, so if we think about this region trapped here, is there going to be a gap? So the only way we can get a disk is if our element is touching the axis of rotation. This element, is it touching that axis of rotation? It's not touching it, right? It's in here. It's inside the region right there. There's our rectangle. It's not touching it, so we are going to get definitely a washer, right? If we were rotating around the y-axis, then we would get a disk, because the y-axis is touching that element. Question?
Do you have like a sheet or like a document of all the formulas for like a volume of a disk or one?
Oh, for the area formulas?
Yeah, like do you have that? Because there's like
There's only 3.
um,
Disk, washer, and cylinder.
yeah.
I don't know if those are on this formula sheet.
But then there's like also finding like the volume.
Well, the volume we find by integrating.
Right, but like for the washer, don't you like and, like
That is just finding the area of the washer, though. The area of the washer is it's the pi r outer squared minus pi r inner
Yeah.
squared.
oh,
So let's see. I don't know if I have those on this sheet or not. I mean, I will write them down every single time, but I don't think I have them over there. Say again?
It says it's like the volume from
In the other here.
Yeah, it's on the top. You can like on the top. It says like the volume of the disc is very at the top.
All the way up here.
Yeah.
Oh,
That's
oh,
kind of
oh.
like the disc and then the one.
Yeah,
below
that's
it.
right. That. Oh, good point. Good point. So right there, yeah, that's the area of a disc. That's the area of a washer, and then this is the area of a cylinder. Yeah, that's a good point.
thank you.
Disc, washer, cylinder. Okay, so let's just wrap this one up. So we've decided it's a washer. We know the area of a washer is the outer radius squared minus the inner radius squared times pi. So it's big disk minus little disk. Pi r squared minus pi r squared. When we look at our picture here, the closer curve is the inner radius. The larger curve, the curve further away, that's going to give us the outer radius. Okay. Both of those are horizontal distances. Horizontal distances, right x minus left x. So when we look at our two curves here, what is the outer radius?
0.
Outer radius is what? Say that again.
0.
Outer radius is not 0. This x value on the right is x equals 4. This x value on the left is x equals 0. So that outer radius is 4. So if we're trying to find this distance from this big green brace here, The x value on the right is 4. The x value on the left is 0. So 4 minus 0 is 4. Another way to think of it, no matter where, so you're trying to find the distance between this left boundary curve and this axis. And those are parallel lines. And those parallel lines are 4 apart. So that's another way to think of it. So when you horizontal distance, right x minus left x. Well, if we're trying to find the distance across here, the right x is 4, the left x is 0, so 4. So that's going to be our outer radius. So that will be 4 to the 2. OK, how about the inner radius? Yes. So let's look at the curve. So the inner radius is going from this x value over here, which is 4. Right? That x value is 4 on this on this axis. This curve right here is y equals root x. That curve is being presented as a y value. If we're doing horizontal distances, we need x values. So we need to rewrite this and say, oh, well, as an x value, that's x equals y squared. So this left x value is y squared. The right x value is 4. So 4 minus y squared is the inner radius. And then we square it to get the area of the little disk. The big disk is the outer radius. The inner radius is the little disk, and we're taking the difference. So our area, let's come over here and simplify this a little bit. We're going to have 16 minus 8y squared plus y to the 4th. Squaring that out. And then we're going to distribute the minus sign and combine like terms. 16s are both going to cancel. And then we will be left with positive 8y squared minus y to the 4th. So that is going to be the area of the washer at y. Does it make sense if you look down here where these two curves, the left curve and the right curve, pinch together to 0? That washer should have area of 0 because that's pinching down to a point, so there's not going to be any discernible area. And sure enough, if we plug in y equals 0, we get 0. The biggest washer is not really a washer either. It's really a disk. Right? This one up here, where this red, that distance right there would be the radius. That should create a disk that has area pi r squared. R is 4, so we should get 16 pi. When we plug in y equals 2, do we get 16 pi? Plug in y equals 2 there, and we get 32 minus 16, which is 16 pi. So that formula is, in fact, finding the area of the washer at a height of y. And our final step will be to integrate from 0 to 2. We want to add up all these washer slices. And if we add up all our washer slices, what do we get? We just have to add those together. Plugging in 2, we get 2 cubed is 8, so we get 64 divided by 3, 32 divided by 5, and then subtracting out 0. So I think the easiest way to do this, instead of multiplying the 64 by 5 and the 32 by 3, I think the easiest way is to factor out a 32. If we factor out a 32, we will be left with 2/3 minus 1/5. And that's a little bit easier to deal with in terms of fractions. Common denominator is 15. Multiply the 2 by 5 and we get 10. Multiply the 1 by 3, we get 3. And that'll be our final answer. So we'll have 7 multiplied by 32. 7 multiplied by 32 is 210 plus 14, 224. Pi divided by 15. All right, any heartache? Yeah, bad question. Any questions? There's always a little heartache when you're learning new stuff. Any piece of this that you want to talk about? All right, let's go ahead and take our 10-minute break. If you have questions, you can come up and we can pick apart this problem. And let's do the torus. Okay, so this is a complicated problem. This will not be on the test, but this is a really good example of some ideas that we are definitely going to be using later in the semester. And it's going to be very common that we have a circle and that we have to either break it apart into an upper half and a lower half, or a left half and a right half, and find the equations of those semicircles. It's going to be very common as we go forward. So this is a good start, a good reminder of how you can solve for a semicircle. And it also gives us a little bit of practice with the washer method. Question?
Are we still at 6.3?
Yeah, this is the last question, last slide in that section. Yeah, last slide in 6.3. So the geometric shape here that we're looking at is a torus, aka a donut. Somebody told me there's donuts out in the hallway, but I didn't see them. They've already been snatched. Okay, so what we're going to do is think about the generating region to build this torus. And if we take this disk right here, so that disk right there, that's going to be the generating region. And if it's rotated around the y-axis, in this case, that's going to create the torus. Okay, so we have as our axis of rotation the y-axis. And at this stage, we don't have shells. We only have washers and disks. So we are going to choose an element. We're going around the y-axis here. We're going to choose an element that creates a washer or a disk, and would that element have to be horizontal or vertical? Exactly. Horizontal, right? Horizontal axis is vertical, so we have to have a horizontal element in order to get a washer. That element is not touching the axis of rotation, so it's going to create a washer. Element touches the axis of rotation, you get a disk. Element has a gap, you create a washer. So that is going to create a washer, right? We have a washer across here. And the area of a washer, we know really well by now. It's pi times r outer squared minus r inner squared. Big disk minus little disk. And so then we have our element, and we come down here and we have to identify the inner and outer radius. So this distance right here, that's the inner radius. So this curve, this is the closer curve. So we're breaking apart this circle into a semicircle on the left and a semicircle on the right. So the semicircle on the left is going to be the left curve. The semicircle on the right is going to be the right curve. And the outer radius is going to be all the way over to there. That will be the outer radius. So the inner radius is from the axis of rotation to the left semicircle, and the outer radius is going to be from the axis of rotation to the right semicircle. We're dealing with horizontal elements. That means x minus x. All right, if we want the distance horizontally, we have to do an x minus x. So that tells us, oh, we're going to take this circle here and we're going to solve it for x. We're going to isolate x. We want to write the left semicircle as an x value. We want to write the right semicircle as an x value. There's the equation. So we need to isolate x. So let's come through here and isolate x. So we have x minus 3 squared, 4 minus y squared. We're going to initiate a square root. So we're going to get plus or minus the square root of the right-hand side. And we're going to get two answers. We're going to get x equals 3 plus and 3 minus the square root of 4 minus y squared. So now we have our two x values. Now let's make sure we understand which is which. What is the x value for the left semicircle? X equals the plus or the minus? So the minus is going to take us to the left. And what is the x value for the right? It's going to be the one with the positive. So that's going to be x equals 3 plus square root of 4 minus y squared. Okay. So now we can build our washer formula. The area for a washer, we know that it's, oh, I already wrote it up there. Yeah, let's just write it again right down here. So it's close by. So area will be pi multiplied by r outer squared. So r outer is going to be the distance from the right semicircle to the axis of rotation. It's horizontal, so it's the right x minus the left x. Well, we're dealing with the y-axis, so the left x is 0, right? The y-axis, x equals 0. So the outer radius, right there, it's just that function. That is the outer radius. That is the distance from this point to the y-axis. Right, so it's that x value minus 0. So it's going to be 3 plus the square root of 4 minus y squared, quantity squared. So there's our outer squared. How about our inner? Is there anything funny with our inner? It's also horizontal. So it's the right x minus the left x. The left x is still 0. So our inner is just the left semicircle. So that's just going to be minus 3 minus square root 4 minus y squared, quantity squared. And we look, we see only y. And that's good because we have a sleeping rectangle which has a thickness of dy. So that's all matching up like we want it to. Y is with a dy. Now we just get to do some college algebra. We have the opportunity to sort of practice our college algebra. Let's come over here because that looks like it's going to be nasty. Okay, so the area of our washer is going to be pi multiplied by. So remember, we're just foiling, right? Nothing, it's just foiling. So we get 3 squared, which is 9. And then it's going to be this times 2. So 6 square root of 4 minus y squared. And then we square that, and that's just going to be 4 minus y squared. So there's the first square. Now we square the second thing. And we have a leading minus. Maybe we'll leave the leading minus and just do it without doing it all in one step. We'll do it in 2 steps. So we're just foiling. So once again, we do 9 and then minus a times b times 2. So that's going to be 6 square root. And then we square the minus and square the root. So we get plus 4 minus y squared. So there's our college algebra. And let's cancel the terms that we can cancel. So the 9 and a minus 9, those are going to go away. And looks like the 4 and the 4 are going to go away when we distribute the minus sign. And then the y squared and the y squared are going to go away when we distribute the minus sign. So the only thing that's left is that root business. So let's see. So that gives us pi multiplied by 6 square roots plus 6 square roots gives us 12 square roots. So that will be the area of our washer at a height of y. All right, any questions on the algebra part there, or the setup, I guess? Okay, so now all we have to do is integrate that, and that'll give us our volume. Can we use symmetry here? We're integrating with respect to y. Do we see some symmetry that we could use? The top half, if we integrate from 0 to 2, we could then double it. You could go from -2 to +2, but if we can have a 0 in the limit of integration, always helpful. So let's go 0 to 2 and double it. So our volume will be 2 times the integral, and we can, well, let's not pull anything out yet. Let's just write it like this for a moment. So this 2 out here is from symmetry. And that'll give us our volume. Okay. So this is going to be 24 pi multiplied by an integral. That is not integrable by you until we learn a technique called trigonometric substitution. But this is, we are able to evaluate it using geometry. Because integrals mean things that are geometric. The integral represents the area beneath the curve that's in the integrand. And what kind of curve is that? A semicircle. That curve is a semicircle. So let's come off to the side and draw a picture of this curve. That curve is a semicircle. This integral represents the area under part of it, and then the integral under the area under 0 to 2. And remember, if we're integrating with respect to y, the word under is in quotes. You know, when the curve is a function of x, under literally is under. But if it's a function of y, under really means between the curve and the y-axis instead of between the curve and the x-axis. So under in quotes when it's a function of y. But we can draw this very easily. This is the semicircle of radius 2. Right? Because if you squared both sides, you would have x squared plus y squared equals 4, which is circle of radius 2. But if you isolate x and choose the positive square root, that's the right half of the circle. X squared plus y squared equals 4, circle of radius 2. If you choose x to be positive root, that's the right half. Okay. Now this says, take that curve and integrate it from 0 to 2, from y equals 0 to y equals 2. So y equals 0 to y equals 2, that's this portion right there. So this integral is representing, this integral right here equals 1/4, right? That's quadrant 1, that's 1/4. 1/4 of the circle of radius 2. That's what that integral represents. It's the area between the curve and the y-axis when y goes between 0 and 2. So that integral, if the 0 to 2 went from, if it instead it went -2 to +2, it would want the whole semicircle. But it's only going from y equals 0 to y equals 2, so it's just grabbing the top half of the semicircle, which is 1/4 of the complete circle. And we know how to find the area of a circle. So 24 pi. Area of a circle is pi times the radius squared, but we only want 1/4 of that circle, so we divide by 4. So this is the volume of the torus. That is it. So this is a good problem that sort of encapsulates a bunch of algebra you should be able to manage, and some Calc 1 where you're geometrically interpreting what the integral symbol means. Integral symbol means the area beneath the curve, where beneath is in quotes if it's a function of y instead of a function of x. Okay, so that's it. That's a tough problem. Now, there is a cool theorem that you will see in Calculus 3 called the theorem of Pappus. You do not need to know this theorem for this class. You probably don't even need to know it for Calc 3. But we're going to talk about it for one moment because it's so intuitive. If you take this generating disk, where is its center of mass? The center. The center is right on the x-axis, right? If you have something that is of uniform density, the center of mass is just the geometric center. And if you have a disk, the center is right in the middle. So what you can do, theorem of Pappus says, we can take the center of mass and figure out how far the center of mass travels. That's going to basically give us an average distance traveled by all the points in the disk. And then we can multiply it by the area of the disk. So if we've got our region and we're going to rotate it around an axis, we can find the area of that region, find the distance traveled by the center of mass, and multiply the two. So let's see what happens. What is the area of this disk? This disk right here, so here's our disk. It's a disk of radius 2. So the area of the disk right there is going to be 4 pi, correct? The circumference, or the distance traveled by the center of mass, is right there. This distance, let's see, that is at 3. So this distance here is 3. So what is the circumference of a circle of radius 3? 6 pi, did I hear? Right, 2 pi r? 2 pi r, 2 pi, the radius there is 3, so 6 pi. And what do we get when we multiply those two together? 24 pi squared. Whoa. Okay, so the volume will be 4 pi times 6 pi, which is 24 pi squared. So just a very cool theorem that will come up from time to time, theorem of Pappus. Makes perfect sense though, right? If you can find the center of mass easily, and then just multiply by the distance traveled by that center of mass, multiply the area by the distance traveled, that's kind of your shortcut. Okay. Theorem of Pappus. Pretty cool. Cylindrical shells. Not as cool, but pretty cool too. So volume using cylindrical shells. So here's what's going to happen. So here's our region. And in this case, we're rotating around the y-axis, creating this bell-looking thing. We want to find the volume of that. And when we look at this generating region, if we wanted to use washers, do you see that we would have to subdivide it into 2 regions, into 2 subregions? We'd be looking here, right? So this region down here has a different right curve than this region up here. You could do it with washers, but you'd have to subdivide it into 2 subregions, which you could do. But here is a cooler thing we can do. We can take a vertical element. So now we're taking an element parallel to the axis of rotation. Axis of rotation, element, parallel, it's creating a cylinder. And so what we can think of is that with our vertical element rotated around a parallel axis, it's going to create it's not technically a cross-section, but it's like a cross-section. It's paper thin. It's a cylinder. And then if we multiply it by dx, then we've increased it to a volume. Then it's going to be like a very thin cylinder, which is the cylindrical shell. And so what we're doing, it's kind of like coring an apple. We're going to find the area of these cross-sections, multiply by dx, so we're getting volumes of slices and then adding them all up. So it's just that our slices, in quotes now because they're cylinders, but they're all going to fill up the volume, create an approximation for the volume, and then we're going to use our Calc 1 wand. Here is our Riemann sum. The area of a cylinder circumference of the base times the height, 2 pi RH. So this right here, that's what this is representing, area of a cylinder. And then that's the thickness of the cylinder. So that takes it from a cross-sectional area to a slice. Slice is volume. Cross-section is area. Add them all up, and then we wave our magic wand. We take the limit of that Riemann sum, and we know by now that the limit of a Riemann sum gives us a definite integral. So there is our definite integral. As n increases, you can see that these slices are better approximating, and then when we take the limit, we get the exact volume. So limit of a Riemann sum is a definite integral. And so our formula, again, very geometric. 2 pi r, so this is the circumference of the base. And then this is the height. So 2 pi RH. Height, if you have an upper function and a lower function, you do upper minus lower. If the lower function is 0, then it's just f. If the lower function is 0. So oh, it says it right there. I didn't have to write it. Circumference and height. So that's our new strategy. Let's see if we can do it. So vertical axis of rotation. The y-axis is the axis of rotation. If we created a horizontal element, we would get disks. But we don't want disks. We want a cylinder. So if we want a cylinder, vertical element. And that vertical element is at a random x. That's a random vertical element at a random x. And when that vertical element rotates around the y-axis, we are going to create our cylinder. So there is the cylinder at x. What is the radius of that cylinder? X. Right? Because wherever we draw that vertical element, we say, okay, that's at a random x. What does that x mean? That x represents the distance from the y-axis. So when that element rotates around the y-axis, it is exactly x units from the y-axis. So that is our radius. So that little x there, let me separate it from the curve. So that is our radius. Right? The radius is the distance from this axis of rotation over to the element. Little r, that's the radius. That is x. And that's all copacetic because we have a vertical element, so we know we're going to integrate with respect to x. If we have a vertical element, the thickness of that vertical element is dx, so we know that everything inside the integrand's got to be an x. So let's go ahead and find the area of our cylinder. Area of a cylinder is the circumference of the base, 2 pi r, times the height. 2 pi RH. And again, our element is vertical. Let me try to make that a little fit. That is our vertical element right there. So 2 pi r, that's 2 pi x. And then how about the height? What is the height of that element? The height of the cylinder. Right, that is what? It is the function. Right? This function, 1 over 1 plus x squared, that's measuring this vertical distance from the x-axis up to the curve. So that is acting like the height of the cylinder at that element, right there. So the function goes in here, 1 divided by 1 plus x squared. So that is our cylindrical area. And if we want a cylindrical slice, we multiply by dx. That takes our paper-thin cross-section into a three-dimensional slice. So it adds some thickness to it. So the volume, I'm going to factor the pi out. And I'm going to leave the 2 in here for a reason. I'll explain the reason in a second. And they give us our limits of integration, 0 to 2. We're integrating with respect to x, which means the limits of integration come from the x-axis. And they tell us that we're going to go from 0 to 2. Okay. This integral is in a form that we need to become intimately familiar with. This integrand is in a form that you may not quite have understood yet. You could do this with u substitution very easily. You would let u be the denominator. That would work. But I want to show you something that is going to be very important this semester in Calc 2. What is the integral of 1 over x dx? Natural log of x, right? Natural log absolute x plus c. Everyone agree with that? So that's a common integral. And the piece that you probably weren't told that's super important is that there's a very special relationship between the denominator and the numerator here. How, anyone know what the relationship is there? What is the derivative of the denominator? And that is the numerator. That is the relationship that is not really looked at carefully in Calc 1 that we are going to look at very carefully in Calc 2. So let's suppose we do this integral with substitution. Let's suppose we're doing that integral. Let's let u equal 1 plus x squared. So then du will be 2x dx. So our volume integral becomes pi integral. Oh, that's just the numerator, right? 2x dx, that's right there. That's the numerator. So we end up with du, bless you, over u. Everyone see that? So u is the denominator, and the derivative of u, well, that's the entire numerator. Now here is an example where we could go to u limits if we want. It's pretty easy, so let's just do it. When x is 0, u is going to be 1. When x is 2, u is going to be 5. All right, and that's natural log of u. So this is pi ln, absolute value of u from 1 to 5. So this is going to be pi times natural log of 5 minus natural log of 1. And what is natural log of 1? Yeah, natural log of 1 is 0. Let's get this under here. So this is going to end up being pi ln 5. So everybody follow that? A lot of steps there. Notice the pattern. So if we look here, we end up with natural log of the absolute value of the denominator, right? That's what we ended up with. What did we end up with over here? Okay, natural log absolute value of the denominator. If we take that pattern and move it forward, so let's suppose at this stage we jumped out. Let's suppose that we didn't convert to u limits. If we didn't convert to u limits, we could go back to x's, and we could use our x limits, which are 0 to 2. Totally fine. This is going to also give us pi times natural log of 5, and if you plug in 0, you get natural log of 1, which is 0. Same answer. So if we look right here, what did we end up with? Natural log of the absolute value of the denominator. Just like we ended up here. Natural log of the denominator. Natural log of the denominator. Same thing. So I am going to refer to this as log form. So this is in log form. Log form simply means the derivative of the bottom is the top. That's what it means. If your integrand is in log form, the derivative of the denominator is in the numerator, and you can cut to the chase. You can leave out 1, 2, 3, 4, 5, 6 steps. You don't need them. This is going to be pi natural log of the absolute value of the denominator. Period. If it's in log form, that's all you do. Log form just gives you a very fast way to get to your answer. And this is pi natural log of 5. So, for example, we can make it look as gnarly as you want. If you have something like, let's go with red here. So, example, if we have the integral of, let's pick a function in the denominator. Let's pick a weird combination of things. Sine of x plus e to the 3x. That's our denominator. If the numerator happens to be cosine of x plus 3e to the 3x, we are done. That is in log form, right? As long as the numerator is the derivative of the denominator, the answer is always natural log absolute value denominator plus c. Every time. So this is another one of those Calc 2 strategies that we need to have in our tool chest. So we've got the reverse chain rule technique. If a substitution is linear, we cut to the chase with RCR. If an integrand is in log form, we cut to the chase by taking the natural log of the denominator with an absolute value. So another super common integral you are going to see over 100 times this semester, something in log form. Very important to be able to do that efficiently. All right, let's go to this problem. Again, rotating around the y-axis, and I want you all to do this one using the shell method. So you've got a model right above it. I'll do a couple of basic setup steps here, but then you can work on it. So here is the cylinder that's created. The radius of said cylinder is right there. The height of the cylinder is that distance. So see if you can find the volume of this solid object created by rotating that region around the y-axis. And also for reference, I'll put over here the area of a cylinder, which you should know by now. 2 pi RH. And as you're working on it, raise your hand if you have a question. I'll come by and give you a tip. A verbal tip, not a financial tip. No 15%. Change the color of these just a little bit. What's the radius of the cylinder?
X.
X.
So you're gonna do 2 pi x times up 1 to
write up the next step while you're working up here, and you can confirm that you did this right. So that is the setup that you should have. Does anyone have a question on that setup? Does that setup make sense? Notice that to find the height, we are doing the upper curve minus the lower curve. And when we do minus the lower curve, we have to distribute the minus to change the signs. Does that all look good to you? Question?
I had a question about why is the radius just some random value there?
So when we pick our visual vertical element, right, we're just drawing it in a random location, right? But there's one thing about that location that's important, and that's its distance from the y-axis. And so we're just going to say if we draw a random vertical element, that's going to be at a random x. If we draw a random horizontal element, it'll be at a random y. So this vertical element is at that location x, whatever it happens to be. And like you're sort of implying that it's a variable, so you can imagine that vertical element at any x between x equals 1 and x equals 4. So if you happen to draw it at 3, then the radius is 3. If you drew it at 2, the radius is 2. If you drew it at 2.5, the radius is 2.5. If you draw it at x, the radius is x. Make sense?
Yeah.
Another question?
No, what?
Sure, go ahead.
So you wouldn't distribute the 2 pi?
The 2 pi, it can be distributed. We can distribute this in if we want, or we can factor out. Since both of these are constants, they can all come to the front. Usually with an integral, it makes sense to bring all the constants to the front, except in one case in particular. If you have an integrand that could be in log form by not factoring something out, there's a case where you usually want to leave the constant in. But most of the time, we want to factor out the common factors. So in fact, some folks will look at this and say, oh, well, let's pull out the -2 also, just to get rid of that and make the integral piece easier, which we can do.
Oh.
You see it? So let's go ahead and do that. Let's factor out the -2 because that's a common factor. That's a numeric common factor. So we could also factor out that -2, and that will make the integrand a little bit simpler. So we would have that if we factored out the -2. Do you have to? No, doesn't matter. It would come out in the wash. So any other questions before we do the integration? Everyone seeing the radius and seeing the height? So the height is a vertical element. Vertical distance, upper y coordinate minus lower y coordinate. The upper y function is that right there, so we're going to take that as upper and then subtract off lower to get that vertical distance. So then we can integrate using the power rule. So we'll get this expression. And then we have the hardest step of them all, plugging in constants and subtracting. It's always hard. But our calculators these days are pretty amazing. They can turn things into fractions pretty easily. All right, so plugging in the 4. So we have 4 to the 4th. One of them cancels, so we have 4 cubed, which is 64. 4 times 4 times 4. Plug in the 4 here. 4 times 4 times 4 again. 16 times 4 is 64. Maybe I'm just going to leave that as a 64 for a minute. And then 16 times 2 is 32. We've got that. And then we subtract off the antiderivative at 1, so we're going to subtract off a quarter. We're going to add a 5/3. We're going to subtract off a 2. So that, did anyone get all the way to the end?
Well, yes, but not correctly.
Well, then don't.
Yeah, yeah. Bad things happen.
That bad things happen? Did anyone get the fraction that this turns into? Or are you going to make me do this? You got 45 pi? 45 pi? Someone else? We definitely should confirm this arithmetic. Anyone else get 45 pi yet? If not, I'll put a little question mark next to it and I'll test. I'll do the arithmetic in my office. Okay, so that's the arithmetic part. So any other questions on the setup? Setup all good? All right, somebody scream out when you confirm or deny the 45. So now let's do a shell method around the x-axis. So we just did around the y-axis. That's the more intuitive direction for a shell. But looking at this region here, and you're going around the x-axis, we can tell right away that a shell makes more sense than a disk, because if we were going to use a disk, we'd have to do two different regions. Because the upper curve here is different than the upper curve there. So it makes more sense to use a horizontal element.
Wait, does that mean that we have to solve for?
So this means that if we're gonna use a horizontal element, we're gonna use a dy, which means we want to solve each of these curves and make them x values instead of y values, right? So as soon as we have a horizontal element there, the length of that horizontal element is a change in x. So we are going to want to take each of these functions and rewrite them as x values. So here we're going to have x equals 2 minus y. And here we're going to have x equals y squared. Good call. And we're going to say that this is the horizontal element at a random y. So we're going to just say, okay, horizontal element, we're going to say that it's at a height of y. So now we go to our basic geometry. Our basic geometry says that the area of a shell or a cylinder is 2 pi RH. Radius. So when we look at this, the radius is the distance that element is from the axis of rotation. That is the radius. What is that distance? Y. Right? That's what this is representing. This is the element at a height of y. That height of y, that is the radius. So, 2 pi y. And now the height. Now the height of this element, it's a sleeping rectangle, so its height is right minus left. It's right x minus left x. That's the height of this rectangle. So the right x is 2 minus y. The left x is y squared. So that is right minus left. The right x is 2 minus y. The left x is y squared. Take the difference. There's your height. Now we can find the volume by integrating. We can factor out the 2 pi. And we'll distribute this y so that we have 2y minus y squared minus y cubed dy. And they tell us that this is a height of y. If we don't believe them, we could set the two curves equal to each other and prove to ourselves that it's 0 to 1. And then we have a pretty routine integral. We can use the power rule. So this integral will become y squared minus y cubed over 3 minus y to the 4th over 4. Then we'll plug and chug. 1 minus the third minus the fourth. That will be 2 pi multiplied by a common denominator of 12. That's going to be 12 minus 4 minus 3. And whatever that turns into. Looks like a 2 will cancel with the denominator, and in the numerator we're going to have a 5, so 5 pi divided by 6. All right, any questions? All right, so we have another one. This one looks like it's a little more complicated. We've got this function. They've already presented it as an x value for us, which is convenient because we are going to use a horizontal element if we're going to create a shell. The radius of the corresponding shell is that distance. The height of the shell is, this distance here. That's the height of the shell. So when that little green element rotates around the x-axis, that's going to create a cylinder with that given radius and that height. So once again, area of a cylinder, 2 pi r, that's the circumference of the base times the height. Radius is y. And the height is horizontal. Horizontal distances, right x minus left x. They already gave us the right x. Very nice. The left x is this 1 over root 3. So the left is just a constant. So it's 4 divided by y plus y cubed minus 1 over the square root of 3. So we've got that. Volume, integrate area. Most of the work tends to be coming up with the right area function. Once you have the right area function, we just integrate it to get to the volume. So let's go ahead and factor out that 2 pi, and then we're going to have an integral. Let's distribute that y. So we're going to have a 4y over y plus y cubed minus y over the square root of 3 dy. And our limits of integration, they give us right here 1 and square root of 3. 1 and square root of 3. So that is our setup. We're going to do a little bit of simplification in this first fraction. Can't we cancel out a y? So this is going to be 4 over 1 plus y squared. And that's going to be another one of those integrals that you are going to need to know. If you look at your integration table, that is an arctangent. That is going to be the most common inverse trig function that you will see in Calc 2 and Calc 3. Inverse tangent comes up all the time for a lot of different reasons. We'll see it a lot when we get to power series. Maybe I'll draw this up here. So the arctangent is a very interesting function because it's one of the first functions you encounter that has 2 horizontal asymptotes. So the inverse tangent function has a horizontal asymptote at pi over 2 and another one at negative pi over 2. And the derivative of inverse tangent is 1 over 1 plus x squared. So we'll talk a lot about the inverse tangent as we go through the semester. At this point, just understand that the integral of, if you know a derivative, you also have a corresponding integral. So if the derivative of arctan is that, then the integral of that is arctan. So that is also in that table of integrals handout. We will see it a lot. Okay, so this is going to end up being 2 pi multiplied by, this will be 4 inverse tangent of y. And then we have to integrate this one. Pretty simple. It's another power rule. So we get y to the 2, add 1 to the exponent, divide by the new exponent. So we're going to have 2 root 3 in the denominator. And this is going from 1 to root 3. Okay, a little bit of trig, refreshing. So when you have an inverse trig function of a ratio, you are finding angles. So when someone says inverse sine of 1/2, the first thing in your mind should be the angle, anytime you see an inverse trig function, the angle that has sine value of 1/2. Or in this case, the angle, inverse tangent of root 3, the angle that has a tangent value of root 3. The next thing we have to think about is the restriction. Inverse tangent is always going to be on the right of the unit circle. Inverse cosine is on top of the unit circle, and inverse sine is on the right. We'll talk about these details a ton. So inverse tangent is always on top. So it's going to go from, oh, I just said that wrong. Inverse cosine is on top. Inverse sine and inverse tangent are on the right. So when we look at a unit circle, inverse tangent and inverse cosine are over here. And inverse tangent can't actually be pi over 2 or minus pi over 2. Don't worry about it right this second. And inverse cosine is going to be on top. So inverse cosine is on top, inverse tan and inverse sine are on the right. So we're asking ourselves, what is the angle on the right side of the unit circle that has a tangent value of root 3? And one of the things that I think is super helpful is when you look at a unit circle and you look at the 12-sector unit circle, so let's just focus on those 2 points. The slope right here is root 3, and the slope right here is 1 over root 3, which if you rationalize it, it's going to be root 3 over 3. So tangent is slope. Tangent is y over x. So when you're looking at terminal rays of the unit circle, the tangent value is the slope of the terminal ray. And so this point on the unit circle is 1/2 comma root 3 over 2, and if you do the y over x, you get root 3. So on the 12-sector circle, the steeper terminal ray has that slope. The less steep terminal ray, it's 1/3 as steep. So that said, inverse tangent of root 3, what angle is this right here? Pi over 3. So that'll be our angle. So this is going to be 2 pi multiplied by 4 times pi over 3 minus, plug in root 3 here. Root 3 squared is 3, so we get 3 over 2 root 3. And now we have to subtract off the antiderivative at 1. Arctangent of 1 means the angle on the right side of the circle with a tangent value of 1. What is the angle with a tangent value of 1? It's the angle that has a terminal ray with slope 1. Pi over 4. Excellent. So we're going to have 4 times pi over 4 plus, plug in the 1 right here, and we get 1 over 2 root 3. So then we just have to simplify this thing. So we'll have 2 pi multiplied by 4 pi over 3. And then minus, let's combine those two. So that looks like it's going to be minus 2 over 2 root 3. And then minus pi. And this pi over here, we can, do the common denominator thing. So we're going to end up with 2 pi multiplied by 4 pi over 3 minus 3 pi over 3 is 1 pi over 3. here the 2's cancel. We have 1 over root 3, which is root 3 over 3. And final answer, we can just get a common denominator of 3, so we have that. Algebra. Or arithmetic, really. Hard part. Okay, so I think this class ends at 11:45, right? Yes. 11:45. Okay, class done. So I will do, so office hours for this class are right after class. I don't think there is another class that comes in here. I do not think. So I'll just stay here as long as people stay up to 12:30. I've got to get back to my office by 12:30, but anyone that has questions can just sit and stay, and I will definitely just answer questions until at least 12:30. Unless we find out that there's a class coming in, but I don't think there is. So today is Tuesday, so see y'all Thursday if you're going to take off. If not, we can do some math. Not all day. Oh, both. Yeah, both. And then I'm in Math Center on Wednesdays from 9 to 11 in the Math Center. Tomorrow morning, 9 to 11. Math Center is down in the library, L2E. So in the schedule, I have it up here. If you go to handouts, right here, the Math Center schedule is right there. And so there's the Math Center schedule. And our class is 2420, so all of the people with the yeses can answer Calc 2 questions. So you can look down there to figure out when you go just to make sure.
So we can go to any of those people that say yes?
Yeah, any of the people that are yes in here, you can definitely get Calc 2 help from. Yeah, and there's more this semester than ever, so, which is great, right? Math Center is a good place to go. So I am in there Wednesdays from 9 to 11. And then Steve can also do Calc 2. Renee has worked with a ton of my students, so she's very good at Calc 2. Yeah, so that's if you want to go to Math Center. All right, see you on Thursday. Have a good one. Say that again, Federico.
I'm not sure
Cody, I think, is only in there on a Friday, and I don't have the Friday schedule up here yet. The Friday schedule just got solidified. He's in there like 2 Fridays.
I didn't see him on there, so I was like, is he,
I think he just chose to do 1 or 2 Fridays. I'll get that piece of it up there also. So,
I heard from someone in one of his classes.
Math Center?
Oh, yeah.
Yeah, he's not in there in general this semester. Question?
45 was good.
45 is good, thank you. Thank you.
Oh,
Oakland Coliseum.
last time.
I've seen a bunch of concerts at the Oakland Coliseum long ago when I lived in Oakland.
Yeah. I have
So
a buddy-
45 is good, so I'm going to erase
Yeah.
I'll erase that question mark then.
Assuming my calculator is okay with no parentheses.
Yeah, I think it's right
I
then.
feel like you should leave the question mark up there just so people can verify themselves.
That's not a bad idea. That's not a bad idea.
Just in case a lot of other people want to make it.
Yeah. Why is... Oh, it doesn't like fingers?
Oh.
I need to use the magnetic pen.
Yeah, I have to use my pen on my tablet when I'm using OneNote.
So there's a little hand that you can click on. So here's what I could have done, which you can do on your tablet. So it's taking my hand as a mouse. If you click on that little finger, then you could do it.
Oh, I don't think I have that on mine.
That little hand.
Tablet.
There should be a way to tell it that you want to use an input device that's not the pen.
Okay.
So
I'll check that
should be
out.
there, yeah.
Thank you.
Something like that. All right, see you on Thursday.
So,
Patrick?
with the shapes, just like
Yes.
how exactly do we know when it's like we're supposed to use like a cylinder or a sphere or whatnot? Because like I know it's like based off the axis of rotation,
Mhm.
but like
So how do we know if we're going to use a cylinder or a disc?
yeah,
Okay, you said sphere, so I got. So a
Just like
cylinder or a disc or a
anything.
washer?
yeah,
Okay, so when we look at this here, So we're told that we're going to rotate this region around the y-axis. Well, the short answer is I will tell you.
Okay, thanks.
I will tell you on the test. Use a disc, use a washer, use a shell. I will tell you. But in general, if you were to look at this, you sort of ask yourself, does the region better accommodate a vertical... Did I stop this?